consider a point P in a plane. If you are to mark another point A, 10 centimeters away from point P, what will be its possible location? Point A can lie at any position on a circle with its center at P and radius equal to 10 centimeters. In this case, the shift in position from point P to point A has a fixed magnitude, which is equal to a distance of 10 centimeters. But it has no fixed direction. We say that distance PA is 10 centimeters. Now, suppose you have to mark point A such that its distance is 10 centimeters from P in the east direction. What will be the possible location of point A? Here, the shift in position from point P to point A has a fixed magnitude equal to a distance of 10 centimeters as well as a fixed direction. In this case, we say that displacement PA is 10 centimeters in the east direction. Quantities like length, mass and time, which are characterized only by their magnitude, are called scalar quantities. Quantities like displacement, force, and electric and magnetic fields, which are characterized by both their magnitude as well as direction, are called vector quantities. Let us take another example of a line L in a three-dimensional space. A straight line extends towards both the sides endlessly in space to an infinite length. If we indicate the direction of line L with an arrow in any one of these two directions, it becomes a directed line. Now consider 2 points A and B on line L. Line segment AB has a fixed magnitude and a direction that is the same as the direction of line L. Thus, AB is a directed line segment. Directed line segment AB is written as shown and read as vector AB. Directed line segment AB can also be represented by a small case letter A with an arrow over it and read as vector A. Point A, which is the starting point of vector AB as per the given direction, is called the initial point of vector AB. Point B, which is the end point of vector AB as per the given direction, is called the terminal point of vector AB. The arrow placed above vector AB always points from the initial point to the terminal point of the vector. The magnitude of vector AB is represented as shown. The magnitude of vector AB is equal to the length of line segment AB. If the direction of the directed line is reversed, we get vector BA. In this case, the initial point is B and the terminal point is A, and vector BA is equal to minus vector A. Note that the magnitude of vectors AB and BA is the same and equal to the length of line segment AB. Now consider a point P in a three-dimensional coordinate system. Vector OP, with its initial point at the origin and its terminal point at P, is called the position vector of point P with respect to the origin. The position vector of point P with respect to the origin can also be represented as vector R. As shown, you know the distance formula to find the distance between two given points in a three-dimensional space. Using the distance formula, we get the magnitude of the position vector of point P with respect to the origin. It is equal to under root of x square plus y square plus z square. The small letter r, written without the arrow, represents the magnitude of vector r. Let alpha, beta and gamma be the angles made by vector r with the positive directions of the x, y and z axes respectively. Then the angles alpha, beta and gamma are called the direction angles of vector r. The cosines of the direction angles of a vector are called its direction cosines. Thus, cos alpha, cos beta and cos gamma are the direction cosines of vector r. By convention, the direction cosine cos alpha is denoted by L, cos beta is denoted by M, and cos gamma is denoted by N. Now, let us find the values of the direction cosines of vector r. Let PA be the perpendicular drawn from point P to the x-axis. Thus, length OA is equal to the x-coordinate of point P. Let PB be the perpendicular drawn from point P to the y-axis. Thus, length OB is equal to the y-coordinate of point P. Similarly, let PC be the perpendicular drawn from point P to the z-axis such that length OC is equal to the z-coordinate of point P. Thus, points O and P lie at the opposite vertices of a cuboid with dimensions x, y and z. In right-angled triangle OAP, cos alpha or direction cosine L is equal to OA upon OP or x upon r, where r is the magnitude of positional vector OP. This implies that the x-coordinate of point P is equal to the product of direction cosine L and r, which is the magnitude of positional vector OP. In right-angled triangle OBP, cos beta or directional cosine M is equal to OB upon OP or y upon r, where r is the magnitude of positional vector OP. This implies that the y-coordinate of point P is equal to the product of direction cosine M and r, which is the magnitude of positional vector OP. Similarly, in right-angled triangle OCP, cos gamma or direction cosine N is equal to OC upon OP or Z upon R. Again, this implies that the Z-coordinate of point P is equal to the product of direction cosine N and R, which is the magnitude of positional vector OP. The quantities LR, MR and NR, which represent the coordinates of the terminal point of vector R in terms of its direction cosines and magnitude, are called the direction ratios of vector R. By convention, the direction ratios of a vector are denoted by the letters A, B and C as shown. Now, let us derive an interesting relationship between the sum of the squares of the direction cosines of vector R. Substituting the values of the direction cosines cos alpha, cos beta and cos gamma from the previous expression and simplifying, we get that the sum of the squares of the direction cosines of vector R is 1. This relationship is true for all vectors. Now, let us see if a similar relationship exists between the direction ratios of vector r. On simplifying the previous equation, we get that the sum of the squares of the direction ratios of a vector is equal to the square of its magnitude. This also implies that the sum of the squares of the direction ratios of a vector is not equal to 1 unless the magnitude of the vector is equal to 1.